This talk is about the good old times. We'll touch, well, almost everything from the old C64. And, well, just let's start. Give a hand to Michael Steil.
Hi. Okay, hi. So, hello, I'm going to talk about the Commodore 64. You may or may not be here because of the whole retro wave. Retro is cool, everyone does emulation, runs C64 on their X serves, has a C64 in their office next to the Mac Pro. There are people who even have license plates with Commodore 64 references. But there's a very important point I want to make here, which is you can do good chip design and bad chip design. And the C64 was a very good chip design. If you compare it to competitors from the same time, like IBM's CGA card, it could address the same amount of memory, but could do graphics like this, and the Commodore could do graphics like that. Or with tricks even like that. And the other thing is, you can be dumb or you can be creative about coding, and if you have to do cycle-exact coding, there's so much you can do, and the question is this an art that has been lost? So I'm going to talk a bit about that kind of programming a machine. These are the topics that I'm going to address. I have 64 minutes, and I have 256 slides. Commodore was founded in 1954 by Jack Tramiel. That's what he looks like today. They made calculators and later bought the company MOS Technology, which is a chip manufacturer. Engineering was headed by Chuck Peddle. This is what he looks today. They made the 6502 CPU originally intended for industrial control, but they also made the KIM-1, which is a computer kit based around the 6502. Commodore thought it would be a good idea to extend that design into a home computer, so the Commodore PET was sold for small businesses and the education market, but they also targeted the home computer business with the Commodore VIC-20, which was a very, very stripped-down computer system, and its successor, the Commodore 64, with 64 kilobytes of memory, which was a lot back then, if you compared it to the market, which was well over $1,000 if you wanted 64 kilobytes of RAM. This is all just the machine, not the monitor or the disk drive. And C64 that sold for just $595 US. There was a successor to the C64, the C128, which was compatible, so it sold pretty well, and the Plus 4, incompatible and didn't sell that well. Between 1982 and 1994, they sold 17 million C64s, so this makes it the best-selling computer of all times, plus there's an extra 3 million C128s. This is what a C64 looks like. There are several models of it. This is the original one. They made an updated, flat version of it and went back to the original design because it was cheaper. They made a golden version, limited edition. They made a portable version, and they made that one. So this is what it looks like if you start a C64. It boots right into BASIC, just from ROM. You can either type in your BASIC program if you want, or you can load something from disk or tape. To give you an impression on the graphics capabilities, this is a very, very early demo by Commodore themselves, the 1982 Christmas demo. Later demos looked more like this, and even later, more modern demos had pretty good graphics, did some 3D effects, or did some other very impressive stuff. Very early games, like Lode Runner, looked like this. Later games looked a little more complex, or even later games used screen modes that weren't originally possible. All on the same unmodified hardware. So let's look at the C64 from the outside first. On the right-hand side, you have two control ports. You can either attach two joysticks or a joystick and a mouse. On the back, you have the expansion port. You can attach pretty much anything there because the whole CPU bus is exported there. Any extension hardware. Mostly people attached extra ROMs there with library routines and extra basic extensions for usability, like the final cartridge on this picture. There's 2 monitor connectors, 1 RF connector and an S-Video-like connector for monitors. The IEC serial bus for floppy drives and printers, tape connector, and the user port for pretty much anything else. So this is what a typical system would look like, a Z64 and a 1541 disk drive on a Commodore monitor in this case. Looking inside, this is the main board. On the left-hand side, you have the CPU, which is a 6510, which is very similar to the 6502. 2 CIA 6526 controllers. These are I/O controllers. And on the right, you have the SID 6581 sound chip and the VIC video chip. So let's go through all these components and let me explain them to you a little bit. The 6502 was designed in 1975 by a team of engineers that had been at the company Moss. They had left Motorola. Engineering was headed by Chuck Peddle, and they're holding the die shot there. The schematic diagram of it, you'll understand it in 5 minutes. This should give you an impression of what the assembly language looks like. Assembly instructions are 1 up to 3 bytes, so it's a 1-byte opcode and 0 to 2 bytes operand. It's an 8-bit CPU, it has 3 registers, the accumulator, which can do arithmetic and logic, 2 index registers, X and Y. They can be used for indexing, can't do arithmetic, but they can be incremented and decremented. There's a processor status with negative overflow 0 and carry and a few other bits, 16-bit program counter, and an 8-bit stack pointer or an 8-bit stack pointer register in an effective 16-bit stack pointer. The upper 8-bit are always confined to 1. So this has some implications on the memory layout of a 6502-based system. The page 0 in RAM is special. I'll talk about this one later. Page 1 is the stack, so the stack is always confined to those 256 bytes. The stack starts at 01FF and grows down. This is an overview of the opcodes that it supports. Out of a possible 256 opcodes, about 150 are available. Let me give you an impression on the instruction set. There are load instructions, store instructions of those registers. You can rotate and shift only the accumulator. You can increment and decrement memory and the X and Y registers. There's addition and subtraction instructions. They always add or subtract the carry as well, so you have to explicitly set or clear the carry. There's Boolean logic, there's compare, and there's the bit instruction. So all these load from memory or from registers, all these are the store instructions. There are some that do direct memory, read, modify, write. These are the arithmetic ones, these are the logic ones, and the column on the left are just like those on the right, but they only change the bits instead of writing back the result. For all those instructions, there are several addressing modes. So depending on which instruction, there are either more or less addressing modes available. The first one I want to talk about is the immediate addressing mode. It's available for pretty much every, or for all the load instructions. You have the hash sign there that signals that it's an immediate load. And what it does is it just puts the value of 17 into the accumulator in this example. Absolute addressing is a memory read, so I have a 2-byte operand, 16-bit operand, so it's encoded with these 3 bytes, as you can see there. And what happens there, I read from 314, it looks into memory, looks at the address 314, reads it into the accumulator. Zero-page addressing is a nice extra feature of the 6502. And a nice optimization. Anytime I want to read from memory, from the 0 page of memory, from the first 256 bytes, it can be encoded in just 2 bytes instead of 3, and it's also a little bit faster. If I load from 2, then it'll look at that address and read that into the accumulator. There's absolute X-indexed addressing, which is intended for reading from tables, from lookup tables. So it first adds X to that address that I specify and then reads from that address. In the example, I read from 200 plus X, so I read from 200 for O2 OA, and O2 OA is 52. I read that into the accumulator. Absolute plus Y, absolute Y indexed is the same thing with the Y register. I have, in this example, I would have an array of up to 256 bytes at that address. Zero page, comma X is the same optimization with a zero page again. Note that whenever I do any zero page addressing or any indexed zero page addressing, it will always stay inside the zero page. So even in this example, if X is above 16 or above 15, it will wrap around to 0. The same is available with zero page, comma Y. And you see in this example that this is a quite rare addressing mode. It's only available for 2 of the instructions. Zero page, comma X indirect treats zero page as an array of pointers. So it first adds X to the address that I specify and then treats that as a pointer and reads from that address. So in the example, I look at the address 80 and 80 plus the contents of X, so it's 8C and 8D. So it reads that, which is C43F, little endian, which is the correct endianness anyway. And then looks at that address and reads that. Zero page indirect Y indexed looks the same, but it's different because it's first indirect and then indexed. So in this case, we only have one pointer at that address and then add Y to it afterwards. So we look at the address 14, and at 1415 we have D800. We add Y, we get D828, and then we can read from the address D828. Because we don't have a single 16-bit register, anytime we have to deal with pointers, we have to store that pointer in zero page and then use this addressing mode. If we don't want to do any indexing, we can always set Y to 0. And then there's register addressing, for example, the shift instructions for the accumulator and the decrement and increment instructions for registers directly work on those registers and don't need any extra parameters. There are register transfer functions between A, X, and Y, and you can also copy the stack pointer between X and the stack pointer. Speaking about the stack pointer, the stack grows down from O1FF. So if I push something, I load something, I push it on the stack, what happens is it stores it at the address of the stack pointer and then decrements the stack pointer. I store another one, so it stores it at the address and decrements the stack pointer. When I pull something from the stack, so I can push and pull the accumulator and the processor status, then it will first increment the stack pointer and then read from that address. Let's do it again, read it, increment it, then read it. The control flow instructions that are supported are jumps, indirect jumps. There's a jump to subroutine, which is a call. So if you know Motorola, you might be familiar with those memos. And there's RTS, which is the return instruction. What's interesting here is that the address that gets put on the stack is the current program counter +2, although a jump is 3 instructions. So when it gets read back from the stack, another 1 has to be added to get the effective address. This is a very interesting internal optimization of the chip. At the top of RAM, there are 3 vectors for interrupts, non-maskable interrupts, as well as the reset vector. The way interrupts work, we can see at the break instruction. Break is the same as an interrupt, but in software. It first pushes the program counter +2, just like in JSR. Then it pushes the processor status and then jumps to over the interrupt vector. You can distinguish between a software interrupt and a hardware interrupt in that you look at the status that got pushed on the stack. There is an extra bit, the break bit, which tells you whether it was software or hardware. And a return from interrupt will just pop the processor status and then pop the return address. So because there's no way to push and pull X and Y directly, this is what an interrupt handler would look like. If you want to save all the registers, you push your accumulator, you transfer